Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Miller, and I'll be your host for today's presentation on leveraging test and simulation to de-risk certification. Please use the Q&A feature in the Teams interface to submit any questions you have during the webinar. At the end, we will address any submitted questions. Our speaker today is Justin McKinnon. Justin is a principal scientist too at Electromagnetic Applications and an industry-recognized leader in electromagnetic effects and space radiation. Justin has extensive test background, having previously served as chief engineer at NTS Lightning Technologies prior to joining EMA. He holds a full authority FAA DER license in all HERF, Lightning, and EMI EMC disciplines, and has played critical roles in certification efforts on dozens of commercial and military programs. He also helped lead the establishment of EMA's Space, Environment, and Radiation Effects, or SERI facility. Justin has significant expertise related to lightning effects on aircraft, wind turbines, and structures. He also specializes in the test and measurement of electromagnetic effects, EMP, radiated effects, and related areas. Without further delay, I give you Justin.
Thank you for the introduction, Matt. Hello, everybody, and welcome to the Leveraging E3 Test and Simulation webinar. As Matt said, my name is Justin McKinnon. I'm a principal scientist here at EMA, and I want to share with you kind of a compilation of lessons learned and things that I've seen on a lot of the programs I've been fortunate to work on. A lot of you that have seen presentations I've given before may find some of the material familiar, and I think that's a good thing, because when you deal with anything in electromagnetic effects, you have to understand why it's so complicated. This domain is unlike a lot of many competing areas, such as mechanical and structures and things of that nature. Most of this stuff is really complicated because it requires integration. And when you consider structural loads as a different and kind of parallel domain there, using simulation and analysis is commonplace. You have to do load and FEM and structure analysis on it. And once you're done with that, you have a high degree of confidence that you're probably going to build something that works. Throughout programs, there's fatigue articles, static shock test articles, things of that nature there. And it's a real focus for many complicated aircraft programs. When you deal with electromagnetic effects, you have to put everything together before you really start to understand if it works. And when you're dealing with the military, you have a direct customer. And when you're dealing with commercial aviation, you have investors and the FAA to contend with, usually your stockholders if you're a publicly traded company, things of that nature. And so lightning and HERF and RF interference and all of these problems require you to understand the structure, understand how the cables are laid out, understand where things are, the external environment, and that's really difficult. Stepping into this industry is also one of the most difficult things that an engineer can do. Practical electromagnetic effects, or E3, isn't taught at the university level. I myself am an electrical engineering graduate. I did my grad and undergrad at the University of Massachusetts. I left school with, I would say, a pretty good idea of circuits and fields and waves, but I had nowhere near the expertise needed to be an effective E3 engineer at that time. And when you're dealing with a program that's spinning up, so maybe you're an eVTOL company making your first airplane, or you're a commercial aviation company somewhere in the middle, where do you get the experts that can drive a program? How do you acquire experience in this area there? And because E3 impacts so many different aspects of the platform, these requirements for E3, when you're dealing with how to certify something for a military or a commercial platform, you have to consider the structures, the materials, the coatings, the installation specifics, wire routing, antenna placement, and it's going to be different on just about every platform. And that coupling is complicated. And so stepping into this field, you're just not going to be productive 99 times out of 100 on day one. unless you know how to attack problems in a simple fashion. And that's really what I want to talk about today. Is what does certification mean, and what tools do you have, even if you're not a world-class expert and you're just getting into this and you want to find a way to do it a little bit better. So certification at its highest level is an additional layer of complexity to the traditional engineering spectrum. For aircraft companies, you have two very distinct jobs. You have to make something that works, which is a technical consideration. That's physics and production and manufacturing. And you have to make something that's certifiable. And your investors and technical folks are both going to be involved in that, because you are not allowed to fly or sell things in the United States without it being certified. People can't use your airplane if it's not certified. And making things work, that's really not as hard as it sounds. That's not to trivialize the design and building of airplanes, but making something work is largely just a programmatic and a technical problem. Put this here, put this there. You can Google and figure things out and find a way to get something that flies. Now, of course, is it going to be safe? That's another challenge, and that's really where certification comes into play. For military projects, that also factors in the ability of the object, being an aircraft in this case, to perform its intended use, as well as another kind of consideration for safety of flight and continued airworthiness. A platform can be designed to be entirely safe, but no purpose is without flaws. And I understand that nothing is going to be perfect, probably as well as anybody, because you have to be able to build it, right? So your designs, every design has tolerances in it, and if you have a million design features all with their own tolerances, there's a million different airplanes you can build, probably a much larger number than that with permutations. And the FAA uses rules and regulations to make things easier to navigate because of how many different variables that there are in how airplanes are put together and the things that go inside it. And all of this comes down to safety. Safety is what drives us to do 95% of the work in electromagnetic effects. We know how to design antennas as an industry really well. We understand how to put airplanes together and make them do really incredible things, fly fast, fly high, fly far. But integrating things together, that's really where it becomes challenging there. And furthermore, I think the FAA would agree wholeheartedly with this statement. People aren't going to fly on something that's not safe. I think a lot of people in today's world haven't grown up with the pains of the 80s and 90s when, accidents like TWA Flight 800, which was an ESD discharge in a fuel tank, blew up an entire plane. We don't have aircraft falling out of the sky all day, every day, which is a great thing. And so, we know that these prescriptive rules and these very strict safety requirements are important. But the downside is that the safer or less risk that you have in your platform, it is almost one-to-one with added costs and reduced performance. If you just add voltage suppression devices and make everything immune to lightning, you're going to have hundreds of those throughout your aircraft, and it's going to cost more. It's going to impact the performance. It's going to, change how things are spaced on the airplane. And all of that is just undesirable when you're dealing with weight and range and things of that nature there. For Mill, there's an additional consideration, not just safety, but the ability to complete a mission, the cost to repair. When you are working on a military program, you are selling a design to the Air Force or the Navy or whoever your end use customer is. And they're not going to want to fix things that are super expensive all the time. So they're requiring a bind or a bounding of the risk that something could happen. So for the FAA, the requirement is 1 E-9 catastrophic events per flight hour, or if you flip that around, it's about 1 billion hours per catastrophic event. Military, because there are generally fewer airplanes and they're not in use as often. Fortunately, we're not at World War for the time being, at least. The military accepts between 1 E-6 and 1 E-7 catastrophic events per flight hour. And those can be accepted, meaning that certain parts of the military platform may have more risk or less risk from a kind of how the airplane is used, or what the fundamental behavior of the airplane is, for example. If you're not going to be flying this thing every day in the most severe environments, or maybe you are, the end use customers in those cases can choose to accept risk. You don't get that benefit in the world of the FAA. But ultimately, the navigation of safety and risk, that's the job of E3. And when we do certification, one thing that I found that I think really bears a little bit more discussion is we are required to certify both type and installation, otherwise known as design and process. One hurdle that I see a lot of our customers run into is they neglect the second part. Our design cannot have paint that is, we want to test things so that they pass. We want to have paint that's, certain thickness. We know that from the lightning standards, thick paint may make all of our test results more severe. We're not going to have that happen. And, I look at stuff like that when you think that you can control your paint tolerance down to thousandths, or down to an individual mil. We just don't see that. Nobody's really been able to do that because there's going to be different people and different machines putting stuff together. And anybody that's worked in a manufacturing environment, such as the one on this page, knows that there are so many different moving parts and so many manual activities on there. And that's why we require statistical significance when you're doing certification testing. It doesn't mean you need to test 100 of something, but testing one doesn't really capture the normal and totally acceptable variability that comes when you build stuff. We've gotten so good at an industry in additive manufacturing and complicated material processes and things like that. But you can never, and I will never believe you when you tell me that any process will ever be perfect. When you deal with fasteners and fuel tanks, you can have a bonding requirement of whatever number that you want to put. Tolerance is going to be dependent on who put it in, the type of fastener that it is, the pressure, the loading that's on it. And you don't want to make a test that makes you pass. You want to evaluate the design. And the passing and failing in things where you have incidental contact, maybe there's not a lot of fasteners in a specific area there in terms of fuel tanks, that could be scary. And you'll get a lot of variability in those results. Flexible fuel couplings are known to be extremely desirable by aircraft mechanics and maintenance folks because they're easy to put on. But we know in the world of lightning that those arc all over the place and they're really, really hard to predict. And when you couple that with brand new platforms, we don't have a service history to know what types of problems our process can yield. We haven't built new platforms in the US since the early 1990s. Everything has been a derivative of an old metal airplane with slight modifications, and until the B-21 Raider and the eVTOL industry and a lot of the current Air Force programs that are ongoing, we're learning on the fly, trying to use updated guidance that committees like the SAE, AE2, and AE4 Lightning and EMI, EMC committees put out to try to make this certification process a little bit easier. The FAA regulations in the world of commercial aviation are what drive us to perform E3. The FAA publishes rules in the Code of Federal Regulations, so these are laws that every commercial certification project, from small aircraft to transport category, Part 25 airplanes, to engines, to helicopters, propellers, will need to demonstrate compliance to. And the demonstration of compliance is what my job as a DER involves a lot of, where I have to make sure that your design meets the intent of the requirements and was tested appropriately and sign off on it there. These rules don't always provide a lot of context. And unfortunately, as with most things in engineering, a lot of your work is in the gray. Nothing is really ever black and white. But through the use of advisory circulars and recommended practices in the FAA regulations, there are some very, very common approaches that are effective in dealing with things like lightning and HERF and electromagnetic interference. To be good at that, it requires you to learn how to read between the lines a little bit and understand what are they actually asking you to do, not what do you think you need to do, but what are you asked to do? And there's some tasks that are pretty easy. Things like lightning zoning. I mean, that process is one that EMA has done for 40, 50 years now almost. And we know it really well. That process isn't going to change. The results might change, but the process isn't going to change from one program to another. But what ends up happening because of the dearth of E3 expertise and experience in the industry there is that companies just start diving into testing, and it ends up kind of leaving a scattershot approach to answering all of the requirements that you need. and can lead to some really painful things to undo later in the project. You can't just start establishing transient design levels, except, well, early in a program, you need to tell your vendors what to design to. So people kind of take a stab at it and don't really take a holistic approach to use modern tools and approaches to do that. And again, that leads to a lot of expensive testing and things that don't need to be done. And I think that there's a lot of room in the industry to get a little bit better at that. Uh, Inside of the demonstrations of compliance, there are some really helpful workflows like line items 1 through 7 here for the compliance to 14 CFR 1306 here, otherwise known as 1316 for bigger airplanes. But in all purposes, it's identify the systems that you need to assess. We need to see what could crash the airplane and what couldn't. We need to look at where lightning can attach on the airplane and figure out how severe or not severe the environment that a piece of equipment may see or the structure may see, and then kind of go through the entire program to figure out how to answer all of that stuff. In the mill world, mill standard 464, it's essentially a lot of parallels with it there. But you'll find, and I've seen this on a lot of programs, that people rely so heavily on quote unquote passing or failing mill standard 461 and DO 160, almost to the point where, I almost advise people not to look at those until a little bit later in the programs, because in reality, you can fail, and I've seen this, you can fail a lot of DO 160 tests and mill standard 461 tests and be a totally compliant, electromagnetically immune platform in the end use environment there. Because ultimately your requirement is not to pass mill standard 461 or DO 160 tests. It's to expose your equipment to the onboard electromagnetic environment and prove that catastrophic functions or catastrophic failures don't occur. And so some people try to do unique stuff. You can certainly do that. You just have to get approval from your customer or the FAA. The FAA doesn't really like a lot of surprises when it comes to things like that. But if you're going to use mill standard 461 and or DO 160 or some of the ASTM standards, those are intended to tell you how to run a test, not whether or not that test is appropriate. And so I think that's an important note to keep in mind here. What isn't spelled out in any of these regulations is what do you do during a program time-wise? When do you do a specific task during a program? And so that's what I'm going to cover, I think, in the next several slides here, and kind of show what I think the correct order of operations is in a program or a platform here. How do you know you've done tasks correctly is the second part there. Who checks your work? You can go do a whole suite of lightning testing or EMP testing and evaluations there and think you're done, but if you present that to your customer and they say, no, you're not done, I mean, oh my goodness, that's quite a bad thing. And, in terms of the FAA, they'll make a ruling of compliance, or your DER will, and your customer will evaluate you against Mill Handbook 516, for example. But there's a lot of intermediate steps in between, and it often seems like there's a contentious relationship that exists between, either the FAA and a platform or like ENEZ, the Air Force, et cetera, there in a program. And I think that dialogue needs to be improved as an industry. Just to make sure that the stories that we are telling, the approaches that we are taking to problems are understood. And we can kind of start to answer these questions before you run a test. Well, during a test, you should have done these 4 or 5 things. And that's really painful. You can't have that happen. You also have to consider the impact of range and performance and weight. And especially in the military world, those can be traded off at times for a little bit more risk. Ultimately, if you need to run an ultimate mission, something that's really, really important, that's going to trump, any longevity requirements at times and things like that. But for both cases, you need to demonstrate your design and process produce a compliant aircraft/platform. And again, in MIL, you get requirements. In FAA, you have laws, rules, and regulations there, and kind of not missing the pitfalls that occur is a big part of that. And as I mentioned, the lack of E3 expertise is still an ongoing problem. Some folks on the call here might laugh, but a lot of the tenured E3 folks that I interface with saw something successful and kind of learned it as quote unquote their way. And they've worked at one company for many years, and that doesn't create a lot of breadth. And, if you're a chef, you don't just work at one restaurant to become a terrific chef. You want to sample cuisine and learn techniques from all over the world. And E3 is very much an art in that practice there. And really the other, kind of downside is that E3 expert can't spend enough time on a bunch of different programs to be able to support stuff. Or the expert works at EMA already, right? We're certainly blessed to have a lot of, kind of major industry participants and experts as part of the EMA team here. Really, one of the worst things that tends to happen is if there is no established E3 expert, somebody gets tabbed. The requirements for things like lightning and HERF and shielding effectiveness, they get passed to people without the necessary expertise. So structures gets handed lightning requirements and they start doing panel testing, systems designers, electrical, and so forth there. And so now you have people doing E3 in kind of a vacuum when, again, E3 needs to be considered as an integration approach. You end up getting testing for the sake of testing because they think it's right. And you don't really get a holistic approach at the design level. People want to everybody's trying to do their job really well, but getting bonding requirements and just having a bond in a certain place there isn't the same as having one that can tolerate fault currents or lightning inside of a fuel tank, for example. And the pass-fail criteria is really one of the biggest parts of a job of E3 is how do you know whether a design is good or not good? Well, you can wait till you start testing. Failing a certification test is how y'all lose your jobs and companies go out of business. And if you think about all the stuff that has to happen before any complex testing can occur, it would really make your mind spin. I mean, so here's some testing that we've supported over the years and have published in a bunch of different locations there. Doing lightning testing on a wing requires you to be able to build a wing, right? So you got to have a design and all the processing and tooling and things like that. And to do HERF testing, HERF should be a demonstration, as should lightning, meaning that you kind of know what you're going to get there. But you find non-compliances all the time, and it's kind of painful because you want to start selling your airplane and getting them up in the air and using them. Your customers certainly do. And so, we again have to build a process around figuring out how to solve these problems earlier so that you don't build up an entire airplane with fasteners that look like the one on the right when they get struck by lightning. All of the various aspects of HERF and lightning interact with different functional disciplines on the platform. And I'm going to keep saying this because it's that important. If you wait until you are doing testing, complicated testing, you're going to miss a lot of root causes. And so if you find that you're getting high cable bundle transient levels during your lightning testing or during your HERF testing, you're getting your swept currents too high, how do you fix that? Well, everything's integrated at that point, and you change one thing, you're probably changing something else, and that's really where you can lose it. So the modern approach. Okay, Justin, you've sufficiently convinced us that you're annoyed to a degree how people do E3. But how do we fix it? Well, the modern approach is to not operate in a vacuum. It's rare, even at the same company, for data to be shared between programs. And that leads to so much rework out there that the test labs in America, having come from one in my past career, we love that. We're happy to test whatever you want us to test. But every program having to start from scratch just drives up the certification timeline, making it take a lot longer and take a lot more money. And that makes the viability of new designs and changes just a really complicated ask. There's a lot of analysis and test data that can and should be shared amongst programs, things like lightning direct effects on skin panels and coating thicknesses and best practices. And you really can't find a good reason, or at least I can't find a good reason why this stuff isn't shared, other than perhaps it's just kind of a breakdown in process. And the sharing of this data really can go a long way to starting the de-risking process a little bit earlier. Every project has some form of functional requirements, which is fly this far or this fast. You want to have these pieces of equipment on it. And you need to flow requirements down to the people. Not all OEMs make the entire airplane. I mean, most of the folks on this call, I think, would understand this well. But you got to go to your trusted partners, companies like L3Harris and Ball Aerospace and BAE and Raytheon and Collins, to design and build pieces of equipment. And you, as E3 or as a platform, have to give them requirements. And so we use these documents like DO 160 and Mill Standard 461 as a way to assess how robust a box is. It doesn't mean that that box won't work on your platform. It's just a way for us to kind of evaluate things on a common baseline and understand whether or not something is going to be tolerant. I mean, if something fails level 1 or level 2 cable bundle testing for Lightning, it's probably going to have a problem. But not passing level 4, we may not even see level 4 on a platform, and the vendors can't know where you're going to put it. You're probably not going to take and put a flight control system, on the outside of the airplane. That wouldn't work too well. So being able to share data with vendors, especially because a lot of these vendors also make airplanes and compete in the same industry there. A lot of companies are very, very unlikely to share design details. So they don't know cabling, they don't know grounding, they don't know routing and bonding. And that puts all of the onus on the E3 folks to relate test data to platform data, and makes a lot of it hard. Two most important questions that you have to ask as you start to go through this when you're looking at this box level data is, what differs between how this unit was tested and how it'll be installed? The structures people or the electrical people may not know all of that data, right? E3, again, is a group that has to look at the whole platform and make sure everything plays nice together. And companies, they want to sell you a box and get that requirement completed very early. To do that, they're going to take, and this isn't a nefarious thing, but it happens, the easiest way to get through whatever their requirements are. And that leads to tons of back and forth. And most of that back and forth differs because we don't really know what the electromagnetic environment is that this box is going to be in. And we won't know it till way later. And so you can either add a ton of cost and make them do something crazy when they're designing the box, or try to use some tools that I'll share in the next few slides here to get to it there. And you also have to be aware of what assumptions they've made. A lot of times when I review test reports and test procedures, you'll find little tidbits, that we're going to ground this locally here. We're going to use a short cable, when maybe on the airplane that cable is 50 feet, 100 feet long. I mean, there's miles of aircraft cabling on aircraft. And, these how the boxes are grounded, where your returns, if they're returned locally to structure or back in the cable bundle, and how many shields are in there. All of that stuff factors into the common mode phenomena that HRF and Lightning pose, for example. And your suppliers just don't know that. And so figuring out what to do with that data is a huge one. The HRF and Lightning regulations are very prescriptive once the safety implications of failure conditions are understood. And so when you're dealing with boxes, you have to, as E3, understand, how does this box fit into the overall operation of the aircraft and the continued safe flight and airworthiness. For example, if you look at the FAA regulation 2513-16, it says each electrical and electronic system that performs a function for which failure would prevent the continued safe flight and landing of the airplane must be designed and installed so that the function isn't affected during or after the airplane gets struck by lightning. The system may automatically recover in normal operation of that function in a timely manner. And everything has to be safe. So this doesn't tell you what tests you need to do, but you need to figure out a campaign or a way to answer all of these questions. And that's the job of E3. If you assign really good requirements to your suppliers, these safety assessments can aid in how critical or how much risk you're willing to accept. If this box provides a function that would be catastrophic if lost, and that, there's obviously, as an airplane or an aircraft platform matures, there's a lot of stuff that you'll learn about how things work, but a lot of the failure conditions, like not being able to brake or being able to control the airplane or getting erroneous or misleading data, a lot of that stuff is stuff you can probably figure out pretty early, and understanding what pieces of equipment are part of that can really move the needle pretty early in the process. You want to try to determine the internal Lightning and HRF environments really early. You want to get that safety assessment done, even if it's incomplete. And you want to start using simulation like a calculator to answer some of these questions. Current density requires only CAD data. You don't need to have any finalized system information or anything like that. You can route representative cables in a model because all we're looking to do is risk reduce. And you can't do any verifications until the end of the program anyways, right? So how do we start to kind of build a process here that takes the lowest hanging fruit and really move the needle early? And so, I use this triangle in my consulting practice on a day-to-day basis here, is that everything is driven by the safety assessment. What stuff do we need to care the most about? And once you have your arms around even some portion of a list related to the safety assessment, you can then determine how much you know about your design, how much experience you have in dealing with that design, and figure out what you need to do. You can either do characterization, and that's if you are doing something you've never done before, or you don't have data you can point to. This is kind of in related to this program doesn't have that data because we did it on a different program. And so I call that no data exists to prove this design will work. Evaluation is where you might do something a little bit more complicated and maybe invest a little bit more time and effort into doing a test or a simulation. And that's really where you have some data exists and we think that this design will work. It's more mature and we just want to prove it. We're trying to get ahead of the really complicated and expensive certification testing so that in the right corner here, certification becomes a demonstration. We are simply showing that we meet the rules. We're not hoping to pass. And if you can get to demonstration with little risk, certification really isn't that hard. And it becomes more of an engineering problem rather than a programmatic one. And that's kind of what we like to see. So how do we do that? Well, start with your preliminary safety analysis. Lean on your safety folks to do the aircraft functional hazards and system functional hazards, and start relating that to your E3 requirements, things like lightning and HERF and HERO and HERP and everything in between there. Do lightning zoning early, and because that's going to tell you where your current density is likely to be highest, right? You're injecting current at the extremities where your initial leader attachment locations are. Stands to reason that those are going to be some pretty severe high current areas. Things that are well shielded and away from direct attachments are going to be a little bit more protected. And so if you have to start making decisions early in a program there, before you've even established your internal and external environments at a high degree, now we can start to do it just with a little bit more intelligence. Getting these preliminary estimates, people just wait until way too late in a program to start figuring out how to answer this. Because what I can always challenge a company on is to say, how do you know this is okay? And you use simulation and analysis in every other field related to building airplanes. Structures does it, aero does it, fatigue and stress and things like that. Those are always done with analysis and simulation. And yet E3 is the one that gets skepticism when you're trying to do it there. And yeah, bad data going into a model leads to bad data going out, but that's the same in every case, right? And so how do we start to build confidence in our analysis and make our testing more strategic and more direct? Well, you have to start somewhere, and we want to do it on things that we can easily validate or verify, and things like the exterior of the aircraft. If you've done lightning zoning, you should be able to kind of do a lot of that with your eyes, unless there's something weird. So after you start, beginning a program here, we want to take a look at defining the stuff that we want to focus on here. And so this is an example of, this is totally made up, but this is an example of what an aircraft hazard assessment may look like. There's a function to provide lift. And so the components that do that are the wings and the control surfaces. And if you lose the ability to provide lift, the aircraft might have uncontrolled descent. That would result in people dying. We can't have that happen. And so what you end up doing as an E3 person is you have to say, could lightning cause this failure condition? Probably, right? I took a lightning strike on the wing. If I upset the systems that operate the control surfaces, if the pilot gets misleading data on the systems associated with flight control, all of that stuff starts to fall out of these. And you can then look at how hardened the box is, how much you know about it, and then place it in the appropriate box that we looked at a couple slides ago. Do we need to do characterization work? Can we start evaluating it and save it for later, or do we think we're good? So what kinds of things do you do during characterization? I like to call these material properties. These are seam and joint characteristics for stuff like shielding effectiveness. Is this area well shielded or not? It's more than just HERF. It's in the world of mill standard, it's whether you get a mill definition for internal or external RF environment. We want all those internal ones because they're lower levels. Lower levels are generally easier to pass. Your bonding requirements. We need to have more rigor in areas that are exposed to the external environment or in a fuel tank. We need to have more rigor in areas with things that are significantly more severe if a failure happens. And we need to figure out, do we have enough fasteners and how are these things mounted? All of that stuff matters. The structural lightning performance. If you have to change the thickness of the skin to survive lightning, you want to know that early because the weight and the strain and the layout of fasteners and the procurement of the materials and so forth there, those are major changes. And so through characterization, we can rule out all the really silly low-hanging fruit that really kind of exists on a platform and make sure that we aren't doing something that we're going to regret later. I always like to call the first order analyses as a key part of the characterization here. And that's lightning zoning, and that's where are things going. A lot of people are remiss to, they try to push back and say that our design isn't mature enough to do simulation because they just don't want to spend the money up front. And, for all intents and purposes, you can spend the money up front or you can spend it later, and it's going to be more money later than it is up front. Stick a box, who cares what the box does, and just stick representative cables in your analysis and just kind of rule out the bad ideas. If you put a box, probably your flight controls are, your flight displays are probably going to be in the cockpit. Cockpit's pretty exposed. Now, do you need it to be hardened to level 3 or to level 4? Well, I can't answer that on day one, but I can certainly tell you that this box that's never been qualified, that's going to have a 10-year lead time, we probably should start figuring out if it's going to be a problem or not earlier than you might think. When you start going in and evaluating optimizations there, you have only so much room on an aircraft to lay things out, and there are major impacts for things like crosstalk and EMI. Your conducted and radiated susceptibilities on a platform are all determined spatially by how things are related to one another. And so this doesn't require you to have a full platform. You can build a simulation of a test bed that you might run. And you can do this for evaluations that aren't even driven by standards. So crosstalk, for example, we want to establish some separation distance for routing guidance and say, we don't want everything to be 8 inches apart, but is 5 inches okay? We can make a pretty educated guess on that and start to make it easier to pass things just by using simulation. And this model, this animation here is, this whole model might take, once you kind of know how to use the tool, maybe an hour to put together. And so that's a really valuable hour to be able to get this kind of information to show that, perhaps beyond one step or the other, whether it matters or not. And building simple test articles can really, give you good inputs to your analysis. For the people that are skeptics, obviously we don't know what we don't know about anything in modeling and simulation. But that's no different than any other domain. And what's awesome is that at least in our domain in E3, Maxwell's equations are spatial, right? We know that if you place things in the appropriate location and they're somewhat reasonable size and shape and separation there, you're going to get pretty good data right off the bat. And then it becomes a factor of putting in key design features, which happens during characterization, and using them. So measuring seam and joint impedances there, looking at the distribution of currents. So if you take a lightning strike on the top of a T-spar or a T-joint, where you have a doubler and maybe you're connecting the skin to a rib, what kind of current's going to make it on the inside? Is this a good, should I move what's bonded to it there? We can answer that stuff, not to state that our design is compliant, but to state that whether or not we think we have risk and need to do more evaluations there. And these tests are not complicated and they're very quick. You should always ask yourself, is it cheaper to run an analysis, use simulation as a type of evaluation, or should we just build a simple test article, right? We don't want to build a model or a test article that looks like the model on this page here, because the more complicated the question, the more appropriate simulation is going to be. You don't want to go build a wing just to start testing and measuring it unless you think it's going to pass, or you have some random access to an airplane that's being used for flight test, right? So, you can't test something until you build it, and that requires a design. But for simulation, all you need is CAD, right? So you have to have, if you're going to be eventually building something, we can build and just take any CAD input that you want from any major CAD activity and build a model of it. And we can poke it and probe it and use it in so many different ways. And again, people are for some reason, they still have a desire to avoid using analysis because they think it's voodoo. They think it's some, made up magic powder process there. When in reality, this lets us peel back the onion and start to interrogate measurements that we can't make until far later in the program. And that's really exciting to me because to see, to have this type of data as a designer, I know that if our lightning zoning, which is done very early, shows that the concentration of currents on this spar is quite high, but it's pretty good. The current density is quite low on the inside there. I know that sensitive boxes there are going to have on the inside shouldn't be installed on the spar. They should be installed on the rib. And you might tell me that's obvious, but sometimes you don't have a choice, right? And you want to make your design decisions with the best available information that you can. And so, the industry is really, and I love this. We call it the MTMI approach. So it's the model, test, model, inform kind of technique here. And if you use modeling like a 3D calculator, you can make your testing better, right? Instead of just testing because you think you need to do panel testing and do lightning stuff, let's be more strategic about it. Let's make a model, maybe, for running a CS 116 or 117 test. And let's figure out what features in the design or in the test are going to have the biggest impact on the results we get. And then let's make sure we understand that. And so you model, you identify what's important for measuring to make sure that your black box, if you will, you have limited knowledge of system internals there, and you make a whole bunch of assumptions and uncertainties there, and just try to inform the test plan. And if you go into a test plan and you assume certain things without having any data behind it there, you can miss and end up getting test results that you can't use. And so, to the purpose of the test at that point is to experimentally measure physical responses. And you run a test. This is something that most of us in the room today probably are familiar with. You calculate and look at what transients you're going to get. You're looking for upsets there. But if you take conclusions from the test and feed them back into the model and validate it to reduce the uncertainties there, you don't need to go back and test as often, maybe not for a long time. And if you iterate that over testing that you're already going to do, you can start to inform or predict how things are going to behave and maybe shift around the order of operations that you're doing stuff there. And that can be huge. Figuring out what gets inside a box and causes an upset, you're not going to be able to run a test and make measurements on the image on the left-hand side here, right? So, if I have a radiated susceptibility test, like RS-103 or something like that, RS-105, pick your favorite one. What physically is causing an upset? I'm not going to know that from the lab. You might have to, monitor it and do something super complicated there. But again, all I need is CAD and material properties, and I can predict where things are higher and where things are lower. And I can use that to assess risk, right? It's really high over here. Maybe we need to improve the shielding effectiveness of my box. I can do that in a design a lot faster than I can in the lab. You can mock up the test setups that you're going to be using. And, we obviously, I'm a fan of the EMC Plus software that EMA develops there, but we can take any number of cables and draw them on a ground plane so that it replicates cable bundle testing and look at how currents are going to distribute and try to figure out what the core wire threat is in a way that you can't do during tests, right? For me to get a current measurement on an individual conductor inside of a large cable bundle, I have to break that cable bundle open, which wrecks the integrity of the shield and makes the data kind of wonky. In simulation, I don't need to break anything. I can just calculate it and get it. And that's a huge advantage when you're out there using simulation. And so once you've kind of done this characterization, you get into the more complicated stuff, right? We have done the first level analysis, the M and the MTMI. Okay, so we know where the current densities on our aircraft are high. and we know where our fuel tanks are. So let's do some arc thresholding there. Let's see if we think at this early stage we have margin, or do we need to start really considering sealants or maybe different fastener styles or something totally different there. And as you do that, you add complexity and fidelity to both your design and to your analyses and testing there. You really start to move the needle really fast. And, this is really where E3 becomes fun. That's where you're not fighting requirements that you didn't have input to. This is where you're evaluating things and you're blowing stuff up in the lab, or hopefully not blowing stuff up in the lab, and running box level testing with good requirements and looking at how to make things better, not make them work. Because when you get to this point, so this is a really old image, but this is what system testing looks like. I mean, you have aircraft representative harness installations, sitting on a bench with a whole ton of current transformers and monitoring and fake software. And these tests can take many, many months. I mean, in all honesty, if you're doing a system test for HRF or Lightning or both, I mean, it's 6 months. You have to get it all set up. You have to figure out how to get it to the lab. You have to monitor it. You have to bring the people out there, and then they're not doing their job. They're monitoring the test. And then what happens if you have an upset? You have to get the level of confidence to a point where this is a demonstration. We are simply just showing that this stuff works. And we've done all of the work that we can leading up to it there. I can run a simulation far faster and far cheaper than it costs to put this test together. You're going to need to do this test at some point. But why wouldn't you make sure that you understand what's going to be going into a box and then make sure the box can tolerate it before you put it here? So the last few slides here, I think, talk a little bit higher, more of a higher level here about kind of how we solve some of these problems. But I think it's important. A lot of aircraft concepts start with a size and shape of a platform and some rudimentary assumptions about materials. This is composite and this is metal. And if we start to do a better job of sharing data here, these really aren't assumptions, right? We can understand that on a previous platform, this type of composite with this treatment there did really well, and we can maybe use it here. But you can use that to make really detailed assessments and again, get data that you can't measure. Right. If I'm worried, how does a HRF functional upset occur? Well, you get, an electric field that induces currents and voltages where they're not supposed to be. And maybe the computer flips a bit. Maybe it makes a bad comparison. It gets a differential voltage. It shorts a TVS out. And you can then use this data to make those assumptions on it. The CAD data lets you get really quickly into the lightning risk areas there, right? Your propellers and the standards and the guidance that kind of exists in the industry, they kind of tell you what to do, right? Red bad, green good, blue good in a lot of these diagrams here. And running a lightning analysis, a full thorough lightning analysis that can be used for certification might be a pretty heavy lift, but getting an estimate of is lightning going to attach here is super important because you have to protect your propeller blades in a design like this. And you're going to need processes and procurement and procedures in place. And so let's do that with a little bit more informed. So when you're on a new program, the last thing I'll leave you with is, where do you start on day one? For me, if I walk into a program and they say, okay, Justin, how do we start to de-risk this platform? I'm going to come in and I'm going to ask, is there anything new or unique that you've never done before or no one's ever done before? New can be, again, new for the company. We've never built something out of composite. This is, a new operating area for us. Maybe we're trying a new enclosure. What is new on this? Because that's where the most uncertainty, not necessarily risk, but uncertainty will live. And then the second is that what critical features you really need to make sure that you work. You really want to use a specific fastener or installation type. Well, let's make sure that we kind of assess that as early as possible. Again, we don't need to wait for the airplane to be built to know that if you put this type of fastener with this installation type or clearance or transition fit or whatever the style is, you can run those in popsicle sticks, really simple, kind of lap joint test articles, and figure out if they're going to arc or spark in a fuel tank before you do an entire full vehicle layout there. If you move into first order analyses of lightning and HRF severe zone, we want to understand what the true risk is, right? Lightning is going to strike everywhere. You have to zone your airplane. But what actually gets to the systems and the components there is not a full assessment there, but certainly an evaluation you can do early. And we can use some rules of thumb, right? If it's on an extremity or edge on the airplane, it's probably close to an attachment zone. And if you believe and if you get experience in E3 that getting an attachment there would be bad, maybe there's equipment that you have to put there. There's some antenna systems, that sort of stuff. Then we can start to do assessments and either move that up in the criticality list earlier in the program, or you kind of push it down if we think it's not that big of a concern. If you're using composites, lightning and composites, they're not as friendly as lightning and metal skins, for example. So if they exist near this first level lightning standard zoning assessment there, these attachment zones are going to define probably where you're going to need the most lightning protection, right? That seems like it's pretty obvious there. So make sure that your composites are well protected and get them into the lab. If you have reason to try to make your composites thinner, or you're using a honeycomb material or something like that, we need to make sure that this isn't going to be a design you have to undo. So go make a square panel. Go to your fabrication partner, your composite manufacturer, and do it. When you look at lightning zoning and you look at things that are exposed to the external environment, maybe there's a transparency or a door or a seam or a joint or something like that. Maybe don't put your safety or performance critical components in that area, right? This is all obvious, but at its core, E3 really isn't that hard. If you break it down into, kind of simple bite-sized chunks here, you can really handle a lot of what people think are hard E3 problems pretty easy. We know from the industry things like joints and seams over fuel tanks, you're going to have to assess that. You're going to have to run testing on that. So why, let's not have it be a surprise when you need to start procuring test articles to do that. As soon as you have an idea of what fasteners and what kind of design features might be there, get those into the lab. Assign 2.5 million bonding values to equipment, please. Bonding is just the biggest misnomer, I think, in all of E3. Oh my gosh, I can't tell you how many times that I've had to try to undo this understanding. A bonding requirement is a functional requirement. You need to have a process in place that results in the installation of equipment in a manner that supports the EMC requirements, so the compatibility of it, as well as the safety requirements there. I can take two pens or two pieces of very, very fine wire and touch the tips of them together and get 2.5 million there. And that has no bearing on the current carrying capacity of that bond. And so, yes, I made 2.5 million there, but that's probably not going to work. And so the number of the bonding value is not important. If you find and you install something in a manner that is a good practice, so the preparation of the surface and the number of fasteners and surface area and contact like that, and then you measure it, that's the number that you should be using. And it's a quality check to know that you performed the installation properly. That bonding number means nothing without process behind it. So I always try to take a second just to harp on that. And in the last couple here, we really need to do a better job as an industry at getting out of the competitive nature with your customer and certification agency. A lot of expertise problems exist at your customer and at the FAA, right? There's nowhere to get this expertise. And so if everybody's vying over the same resources at a company or at an industry there, it behooves us to try to work together and kind of crowdsource that expertise wherever we can. The FAA's job is to help you, whether you believe it or not. They want you to certify. That's their job. They're just going to make sure you do it safely. And a lot of people don't want to talk to the FAA because they're worried about something that they really have no control over, or that they think the FAA is going to do. And the MCO and your military cert offices, they want the product. They're the ones who are out there giving out the big contracts and making sure that the fighter jets of tomorrow and things like that are built. And so you shouldn't be surprising your customers with the way that you do things. So get those conversations going early and get them going often. And the last slide here that we'll pause, I think, for a couple questions is that you want to do all that you can to make sure demonstrations are only demonstrations when it comes to compliance. And to avoid all of the rigor and cost and schedule stuff there, you need to be able to push back at the managerial level, because I have seen too many times that managers and the bookkeepers of the world, they try to get away from doing things differently because it seems like cost, and they can cut a corner and they can make things a little bit cheaper there. Testing is expensive. We don't want to do that simulation. We did this on this other platform this way. And, doing things the right way is expensive up front and really cheap later. And doing things wrong might be cheap now, but the cost later is a lot. That's for both commercial and for mill programs there. And so at the Expo, EMA Expo last year, we talked, we gave a course on how to do these sorts of things. We have the EMA Expo this year that's coming up in April that, many of you will probably start seeing stuff in your emails about. We don't want to get down in the weeds of certification there, but survivability is kind of the key with it there. How do we make platforms survivable and do so in a way that really kind of takes the guesswork and a lot of the cost out of doing it there. And so that's it for me. Thanks you guys for listening. If you got any questions.
Yeah, thank you, Justin, for that really informative presentation. We do have some questions from the audience. We'll start with the first one here. And by the way, if you didn't catch it earlier, there's a Q&A button at the top of your Teams webinar interface. So if you click on that, that will allow you to submit questions. And we'll get to as many as we can, but we do have to stop at the top of the hour. So the first one here, I feel like you addressed this during the presentation, but let me just put it out there. How can you give good E-cubed requirements to a vendor on a new program?
Oh, that's a great question there. And I think, I did touch on it a little bit, but it's probably worth explaining just a little bit further there. You have to be able to tell the dialogue between an OEM and a vendor needs to be open. And that means that you need to tell them to test and report, not test to pass. And that conversation, I think, is something that really needs to be happening better. Because as an E-cubed, engineer, you want them to tell you at what level does this box start having problems, right? I mean, maybe it's not level 3. If you go out and measure some level in between level 3 and level 4, what do? Right? So a lot of that stuff is really, kind of a dialogue thing. But when you're giving requirements, think about where in the airplane it's going to be and use some of the guidance that exists in, kind of the literature that's out there for the mill standards. And, don't be afraid to be a little bit less conservative, I think, than you want. I mean, making vendors pass exorbitant requirements only to find that you don't see that environment on your platform there is just, man, that's a lot of money and a lot of time that you don't need to spend. And so what I like to do is use simulation as early as I can to get an assessment there. Again, run something on notional CAD. It doesn't need to be a replica. And then kind of drive those requirements with data rather than kind of hopes and dreams.
All right. Well, thank you for that answer. Next question. Is there a pathway for incorporating E-cube simulations into the FAA certification process documentation? And then it goes on to say specifically, is there an ARP or advisory circular that outlines requirements for using simulations as an alternative to coupon testing?
So I don't think that certification in general will ever move away from pure testing. I can speak from my own experience in doing this. The SAE is putting together a simulation for certification document. EMA's own Cody Weber is heading up the development of that. But for all intents and purposes, you really have to treat it the same as test data. On a previous program, we need to assess we had to do this for a fuel tank. You need test data to do characterization and show that your model works correctly. And you need to have enough measurement points there to give a breadth of confidence and show comparisons between the model and testing there. And the benefit of doing that in lieu of testing isn't seen on the program that you do it on. It's for follow-on ones is really where that cost goes. And so on that platform, we did Zone 1A wing testing and made a bunch of measurements on cable bundles and structural current densities for Zone 1 and Zone 2. And then they might have made another derivative of the aircraft that we wanted to use the similarity argument for. And because we had that model, we built a model that replicated the wing and the fuel tank there. We were able to take a program that spent many seven figures of test costs and analysis costs and do it for a few $100,000, where you're only testing the deltas rather than testing kind of everything from scratch and repeating effort there.
Okay, thank you. One last question, and then we're going to wrap up here. Does the EMC Plus tool include a feature to parameterize components for evaluating different scenarios based on various configurations of the type design as a risk forecasting exercise? And then it goes on to say, could you comment to whether some clients, OEMs, have requested this capability in the past?
Yeah, we use scripting for the vast majority of the simulation work that we do at EMA, and so our Python API interface in there really lets you kind of go in and automate whatever it is that you want. For when you're running a sim, the user interface just generates a file, a description that our solvers kind of consume, and so to go through and automate things. The scripting can update the emin files or what they're called, and automate it that way. You can batch and set up a whole bunch of simulation files with different scenarios and kind of just start it on a Friday and come back on a Monday. All of that stuff is kind of commonplace in the way that we work, but it's kind of left up to the user to how you implement it, if that makes sense.
Okay. Well, let's go ahead and wrap up here. As a reminder, any questions we didn't get to will be addressed via email. You will also be receiving an email from us with a link to the recording of this presentation. If you have any questions about anything that Justin talked about today or EMA as a company, please feel reach out to Justin directly or through the EMA3D.com website. There is a contact us link on our website, and we'll respond to that very quickly and get you to the right people. Next up in the EMA Solving Electromagnetic Challenges webinar series is PCBA Designs, Importance of Early Signal Integrity and EMI Reviews, and that webinar is scheduled for January 22nd. Thank you very much for your time and attention today, and we hope you have a great rest of your day.